let's talk about gases. So let's say if we have a container and it's filled with many types of gases. Let's say the green dots represent one type of gas, and let's say the blue dots represent another type of gas. So it's a mixture of gases. Now, both these types of gases will be exerting a pressure on the container, right? Because when the gases bump into the walls, they exert some sort of pressure on the container. And it turns out that the total pressure, so basically the total amount of pressure that's exerted on the container, that's going to be equal to the pressure that is exerted by the blue particles plus the pressure that is exerted by the green particles. And you can kind of be like that kind of makes logical sense, right? Like each individual gas particles of some sort of type, right? Each type of gas particle is going to exert a different pressure, could be the different pressure, could be the same pressure, but it's going to exert its own pressure, right? And if you add all of these independent pressures up, you get the pressure of the total thing, right? Because each type of gas molecule or gas particle, that's going to contribute to some sort of pressure. Now, we have something known as a mole fraction, and it's pretty much exactly what it's exactly what it sounds like. It's basically the amount of moles you have of something over the total amount of moles there are. So it's like a mole fraction. So for example, if let's say I have a container full of gases, let's say that if I have 3 moles of N2, and let's say that the total amount of moles of gases there's 6 moles in total, or let's say there's, I don't know, 8 moles in total, right? Well, the mole fraction is just basically the ratio between the amount of gases sort of you're focusing on. So in this case, there's 3 moles of N2 divided by the total amount of moles, 8 moles total. So the ratio of basically N2 to the total amount is 3 over 8, right? And yeah, N2 makes up 3/8 of pretty much the total amount of gases there are in this container. Now, it also turns out that the amount of moles you have is pretty much going to be proportional to the amount of pressure that it exerts, right? I mean, that kind of makes sense, right? The more moles of A that you have, right? The more moles of some gas that you have, well, the higher the pressure is going to be. And this is Avogadro's law, which basically says that pressure is proportional to the amount of moles that there is of that gas, right? If you have more gas particles in the container, more of it is just going to bump into the walls. Therefore, the pressure is going to increase, right? If you increase the amount of moles of A. Now this equation right over here is a pretty nice equation. This basically says that the moles of A divided by the total amount of moles is equal to the pressure that's exerted by A divided by the total amount of pressure. Let's apply this to a practice problem. So you have 2 moles of this, blah, 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 blah. The total pressure is this. Let's find the mole fraction of each gas and the partial pressure of each gas. Okay. Notice how there's 2 moles of O2, 3 moles of N2, and 1 mole of CO2. If you add all of these values up, you get that there's 6 moles of gas in total, right? There's 6 moles of gas in total. What's the mole fraction for O2? Remember, the mole fraction just represents the moles of A over the total moles. So 2 over 6 gives you 1/3. This just represents that O2 makes up 1/3 of the total amount of gas that's in this container. If we're talking about N2, well, then we do 3 divided by 6, right? 3 divided by the total amount, and we get 1/2. This just shows that N2 makes up 1/2 of the gas in this total container. And if 1/3 plus 1/2, right? 1/3 plus 1/2 is equal to 5 over 6. Well, then the amount of the mole fraction for CO2 should be 1 over 6, right? Because 5 over 6 plus 1 over 6 gives me 1, aka 100%, aka 100%, right? If you add all of these gases up together, right? If you add all of these mole fractions up together, you eventually get 100%, right? You start out with 100%. Each one of these makes up a fraction of that 100%. If you add all of these values up, you get that 100%. All right. Now, let's find out the partial pressure for each gas, okay? So the partial pressure for each gas. Let's find out the partial pressure for O2. So in this case, you can also use the equation, the mole fraction is going to be equal to the pressure of A over the total pressure, right? Because remember, the mole fraction is equal to this, right? The moles of A over the total amount of moles. And the moles of A over the total amount of moles is equal to this. So therefore, this has to be equal to this, right? All of these are equal to each other. Now, what's the mole fraction for O2? Well, the mole fraction for O2, remember we said that was 1/3, right? Because it made up 1/3 of the total amount of gases there are. And that's going to be equal to the pressure exerted by A. So we don't know what the pressure of O2 is, right? Because remember, each gas exerts a partial pressure, right? Something known as a partial pressure, basically the pressure exerted by just this one type of gas, right? When you add all these partial pressures up, you get the total amount of pressure. We don't know what the pressure of O2, we don't know the pressure that the O2 molecules exert on there, but we do know that the total amount of pressure is 600. 600 this. All right. Now that I have wrote this out, I can just solve it. And when you just solve for x, you just cross multiply, divide by 3. But you get that x is equal to this. Just write this all out. Okay. This unit, by the way, is called millimeters of mercury. It's just another unit for pressure. So it's like ATM, right? Some stuff like that, right? Units for pressure. This is just another unit for pressure. Now notice how because O2 makes up 1/3 of the total amount of gas there are, it exerts 1/3 of the total pressure. All right, so like this formula right over here, or this formula, I like to think about it as like the mole and pressure ratio, right? If you make up 1/3 the amount of moles in this entire container, you're gonna make up 1/3 of the entire pressure. That makes logical sense. If we do N2, right? Let's try to find out the partial pressure for N2. So N2, remember we said that has a mole fraction of 1/2 because it makes up 1/2 of the gas. So if I set up the same equation and I solve for x, I get that x is equal to 300 millimeters of mercury as the answer. Notice how, because it makes up 1/2 the gas, well, it makes up 1/2 the total amount of pressure, right? And we can do the same thing for CO2, but we don't have to, because remember that the total amount of pressure, right? The total amount of pressure is equal to 600 millimeters of mercury. We know that O2 has a pressure of 200, makes up a pressure of 200. We know that N2 makes up a pressure of 300. So if we're trying to find out how much does CO2 make up the pressure of that entire container, well, we know that the total pressure has to be 600. So 200 plus 300 plus actually 100 millimeters of mercury will make up the total amount of pressure in the container. So therefore, the partial pressure for CO2 is 100 millimeters of mercury, right? So this is kind of how you apply these two formulas right over here, right? If we know the total amount of moles, if we know the total amount of pressure in the container, and we know the partial pressures for each of these individual gases, and there's only one gas left, well, we know that it all has to add up to the total amount of pressure. So essentially, you could just solve for x in this equation and get the answer. Let's take a look at this problem. You have a rigid 10-liter container, 300 degrees Kelvin, contains a gas mixture made of this, and this. Calculate the mole fraction of each gas. Find the total pressure of the mixture, and find the partial pressure of each gas. Oh, what the hell? This is giving a lot of information. Why do we need to know it's a rigid 10-liter, 300 degrees Kelvin thing? Oh, I know why. PivNert, you know what I'm saying? PVNRT. Got to use the ideal gas law. All right, that's your little hint. If you guys maybe pause the video and try to solve this yourself, that is the little hint. Now remember that mole fractions got to be in moles, right? So we have to convert grams to moles. Now remember that H2. So we have 2 grams of H2, and remember that H2 has a molar mass of 2. So for every 2.00 grams of H2 I have, that's equal to 1 mole of H2. So therefore, 2 grams of H2, that's the same thing as 1 mole of H2. If I have 56 grams of N2, what you have to realize is that what you have to realize is that for every 28 grams of N2 there is, right, because the molar mass of N2 is 28 grams. And if you did not know that, well, I just know that the molar mass for nitrogen by itself, like a single nitrogen, is 14 grams per mole. So if I have N2, well then I have two nitrogens this time, so the molar mass is going to be 28 grams per mole, right? So in this case, the molar mass for nitrogen is 28 grams per mole. Grams cancel out, and you get that this is the same thing as 2 moles of N2. Finally, CO2, it should have a molar mass of 44. So I'm just doing it here, but it have 88 grams of CO2. We know that it has a molar mass of 44 grams. So for every 44 grams of CO2 I have, that's the same thing as 1 mole of CO2. So then I get 2 moles of CO2. And yeah, I should round to the correct number of sig digs actually. So this should be 1.00. This should be 2.00. But you know, I'm not going to write that out because I'm a little too lazy today. I'm sorry, guys. All right. Calculate the mole fraction for each gas. So how do we do this? Well, in this case, we have 2 moles of CO2. So let's calculate it for CO2, H2, and N2. So notice how there's 5 moles of gas in total. 5 moles of gas in total. So the mole fraction for H2 would just be 1/5. The mole fraction for N2 would just be 2/5. Mole fraction for CO2 would just be 2/5 as well. Notice how all these values add up to 100%, right? So that's how you can check your work. Find the total pressure of the mixture. Okay, Bivner time. We're trying to find out the pressure, so we don't know what the pressure is. We do know that this is going to be multiplied by the volume, 10 liters, 10.0 liters. We also know that we have N right over here. N represents the amount of moles we have. In this case, we have 5 moles in total. So we're going to take our total amount of moles and we're just going to plop it in there. R, 5 moles. R, that's going to be a constant. So it should be 0. And then this is going to be divided by moles times Kelvin. So yeah, moles times Kelvin. And this is going to be multiplied by, so then we have temperature, 300 Kelvin. So 300 Kelvin. If we're solving for pressure, let's just divide by 10 liters on both sides. 10 liters on both sides. All right. Now, notice how liters cancel out, moles cancel out, right? Because this is 0, this is 5 moles, there's moles here. Notice how Kelvin cancels out. And notice how we're left with ATMs as our unit. ATMs is a unit for pressure. So if we're just left with the unit for pressure and we're solving for pressure, that's how we know that we've done things right. So I'm just going to use my calculator here. So 5 times 0.021 and then multiplied by 300 and divide by 10. Should get, I'm going to round to 3 sig digs because remember this 5 moles right over here? It should have been 3 sig digs because that's what we started with originally. So yeah, I'm just going to do 3 sig digs. So 12.3 ATMs as my total pressure. All right, this is the total pressure, P total. All right, because we used the total amount of moles in our ideal gas law, right? We use N total. Well, that's just going to give me the total pressure. All right, now that we have the total amount of pressure, we can use our mole fraction formula to kind of do this. So remember, the mole fraction for H2 is 1/5. We know that we're trying to find out the partial pressure, right? The partial pressure of H2. We don't know what that is, but we do know that the total pressure is 12.3 ATMs. So we know that H2 is going to exert 1/5 of the total pressure. So what is 1/5 ratio? So 12.3 divided by 5. That's going to be 2.46 ATMs for hydrogen. And we have 2/5 here. So we do the same setup pretty much, except that we have 2/5 is we do 2/5 is equal to this. And after that, when we solve this, you should get 4.29 ATMs. You should get 2.49 ATMs for both nitrogen and CO2 actually, for N2, and then 4.29 ATMs for CO2. And the reason why you should get the same answer is, remember, the mole fractions are the same. Both these gases make up 2/5 of the total amount of moles there are. So if they make up 2/5 of the entire moles, well, they should make up, both of them should make up 2/5 of the entire pressure. So their pressures should be the same. And if I actually add all these values up together, so if I add up 2.46 plus 4.92 plus 4.92, notice how I get back to 12.3, which is the total amount of pressures. Remember, all the partial pressures added together should lead you to the total pressure. That should, kind of make sense. Okay. And another way you could have done this problem, if you wanted to calculate the partial pressure of each gas, what you could have done is you could have done the ideal gas law before every single one of these moles. So remember how when we plugged it into the ideal gas law, we used the total amount of moles there are, right? We used 5 moles and we got the total pressure. However, if we only used, let's say, 1 mole instead of 5 moles, we would have gotten the pressure for H2. Because remember, H2 makes up 1 mole, right? So what you could have done here is you could have plugged into the ideal gas law each individual amount of moles, depending on kind of what you're dealing with. So you would still get the same answer, but it would just take like a longer time. So this is why you would use the mole fraction part, right?